Yeah, so I already see something that I wanted to announce about the assignments and groups. So first point, which Patricia already raised on chat is, are people still looking for groups? Teng Teng shared a Excel sheet, Google sheet, on which if you have already formed groups, you should enter your names, your name and your teammate's name. You can also do solo if you don't find a group. But do form groups, because I think by the time you submit assignment 1, you certainly want to have a group, because that's what's gonna persist for the rest of the semester. Okay. So I see a couple of people are trying to form groups. So maybe I don't know if you can chat with each other privately, maybe on through this interface. I try to see if want to have try to have a meeting and see if your schedules fit and so on. If you want to and maybe form a group. Okay. And of course, if you're not able to form a group, email Teng Teng and myself. We did hear probably from one person, but hopefully within the next week, as the assignment deadline is next week, things will get resolved. Okay. So with that group formation aspect, the second part is about assignment 1. I hope all groups, or all, at least everybody has looked at assignment 1. And I know some of you have already started doing a few initial questions there. Uh, is there any questions related to that I can take at this point? If somebody has an immediate question, I can answer right now.
I have a question. This is George, by the way. I have a question. I would kind of talk about it at the end of class. I have to show you something from my laptop in order to clarify. So bear
Yeah,
with
yeah.
me, please.
Yeah, definitely. And as I said earlier, I'm gonna hang around on the same Zoom link after the class. So if folks are interested, just queue up and we can discuss, get into your code. There's a point about points being low. Actually, each assignment is about 8 points. So it's really not the magnitude of the points. So each assignment is 8% of the whole grading scale. So even if I scale it up by 10, let's say it's 25 points per question or something like that, it ultimately it just comes down to 2.5 or whatever points once you add up everything. Okay. So a big chunk of your grading, I believe, is also on project. So, but if you do fine on assignments, a project at the same level or a little bit higher level is easy to accomplish. And and also the expectation is that you don't jump onto projects right now, but once you get seasoned into a couple of assignments, you have a much better idea of what's ambitious, what's not too ambitious, and so on in terms of project outcomes. Okay. So let me resume where we left off. Actually, we were planning to. So we are a little bit delayed in terms of the plan I had in terms of topics to be covered, but that's fine. So today we'll look at. So today we'll look at um, this section, which is this module. Let me open it up in a second. Um, wow, I'm using Internet Explorer and it's not opening. Okay, great. Okay, yes. I don't think that was the right link, but okay, let me just drop this part. Oh, wow. I think I should. Sorry, I just rescaled the window because it's just overlapping with the other. I just got my hand on the Windows environment for other reasons. Okay, let's see. How do I? Okay. Backend error. Okay, well, it worked this time. Yeah. Sorry, I just wanted to show you the motivations before I jump into the content for today. So where we left off last time was about was at the point where we were looking at a script which was implementing multi-class logistic regression. Okay. So folks who have looked at multi-class logistic regression or logistic regression even for two classes, maybe in 572, maybe in some other course, or in a course in parallel to this, I would suggest reconciling what we saw, or at least on the code, as well as even in the description of the first set of slides. It's actually multi-class logistic regression. Okay? So I would really encourage you to reconcile the, we are using a slightly different set of, I guess, notation or symbols, like W comma B. So I would suggest reconcile it with things that you might have seen in other courses. Okay, and so that's where we left off last time. Let me just see chat a second. Yeah, I guess folks are talking about group formation or discussion. Yeah, we can also have a discussion board. I believe there is a discussion board capability in Blackboard, but I have not explored it.
Professor, what about Slack? Slack is better, right?
I did experiment with Slack last time. What happened is not not much response. So it just it's just a question of momentum. I can set up Slack if folks are interested, but I did try last time and it was not that effective. But yeah, whoever suggested, why don't you drop me an email and we can set up a Slack and see if that's helpful for
Yes,
um,
Professor.
yeah.
I'll do that.
Yeah. Okay, sorry. I was okay. Where was I? I was talking about what we saw last time: multi-class logistic regression, and and looking at that code base is very useful because that's an integral part of trying to do assignment one really well. Okay. So, for example, the way the script is laid out, you can kind of mimic that if you have not done it before. For example, the regression problem in question number 2. Okay, in assignment one. So let me come back to what we're going to do today. Today, the objective is we actually did a part of today last time, which is we briefly looked at some Python, syntax and the core data types. As I said, if you just get comfortable with, hey, how do I use a dictionary? How do I use a list? And how do I, use a tuple or a set, if needed, then you can pretty much do many of the things that you have probably seen in with R or elsewhere. And of course, the strength of Python ecosystem lies in using packages, and you'll see that from assignment 2 onwards, you will tend to use certain packages. For example, TensorFlow or PyTorch. Today we'll look at today's goals are as follows. So there are three goals. The three goals. First is we'll look at the most basic neural network model class, which is the fully connected or feed-forward neural network class. Okay, and here, this class is just for us to get acquainted with the mechanics or the internals of this model. And in particular, we look at what are hidden layers, what are nonlinearities, what's a neuron, for example. Okay, and then we'll move on to start talking about a new class of uh, neural networks, which is called class of convolutional neural networks. Okay, so there, I guess the new component will be there'll be a layered view. Okay, we'll also see layered view in when we're talking about just feed-forward networks. And then in convolutional neural networks, the new addition would be a new layer called the convolution layer. So that's it. So step one is to understand, hey, what's the layered view of this model and what are nonlinearities and stuff like that. Step two is to say, let's look at a new layer. And the new layer is motivated by motivated by its application for image data, the unstructured data that we had briefly mentioned in the previous two sessions. And there's also going to be a couple of other tricks like what's called pooling and so on. Okay, so we'll look at those things. So at the end of this session, you want to kind of get a feel for both feed-forward neural networks and convolutional neural networks. Okay, and just, hey, what's the simplest model? And we're not talking about uh, really complicated models. So as long as you can understand the layer view for these two classes of models, then it will help, certainly as we go forward with more interesting architectures. Okay. Okay. So let's talk about feed-forward neural networks. So every time, I'm using this, and we've seen this notation last time. I've been using this, sorry, let's say, I've been using this, like symbol F with, let's say, X and W and B last time. Okay, so this was, in Python, and in assignment 1, you would generally define it as like def. Okay, model takes as an input X, may already have, some parameters inside, like W and B are already in the definition of this function, and you return something like W times X plus B, for example. And this will be like basically this will be for example, a 3x1 dimensional score vector. Okay, 3 scores for 3 classes. That's what's the running example last time. So this notation just means this is a model. Okay, loosely speaking, these two are the parameters. Okay, W and B. X is the input for any input X training or X test. For X training, hopefully this model predicts. In our running example, there was 3 scores, S1, S2, S3 in a 3-class classification setting. For training example, let's say X training, or one training example, hopefully the score for the correct class is the highest. Okay, that was the hope, and we were trying to pick W comma B such that this is the case, that the score for the correct class is highest. And then maybe for X, let's say test or something like that, it does optimized W comma B. This F is very close to whatever was the Y test, whatever should be the true label for that class X test, for that example X test. Okay. So this is a notation. This is the notation for the model. What we're going to do is really use diagrams in most of this lecture to expand out this small notation here. Okay, and we'll do that with starting with feed-forward neural network, and then you'll see that logistic regression that we saw last time is also a very special corner case or special case of feed-forward neural network. Okay. And so with that, let's start. So this model here, so as I said, the model f of x is basically wx plus b, and this is what I was saying is multi-class logic regression. You would also call it just as a linear model. Okay, that's linear model because it's linear. It's it's linear in the parameters, right? So it's linear in it's a linear model because it's just performing a linear transformation. In fact, it's a linear transformation plus an offset, so it's basically called an affine transformation, but doesn't matter. So it's just you are linearly changing the x. So if I change x by 1 unit, the output roughly changes by the same scalar, same type of a proportional way. Okay, and that you can see, that any matrix multiplication, a matrix is a linear transform. I mean, a matrix is a representation for a linear transform or a linear function. Okay, a linear model, linear function, linear transform, all of them are the same thing. Okay. But this is the core of logistic regression. Okay, so just this is not logistic regression. This plus that loss that we chose, remember, there was a minus log of the probability of the true class, with some softmax or some logit operation going on with the scores. And so that this linear model plus that loss function together is basically multi-class logistic regression. Okay, so but if you don't recollect much about multi-class logistic regression, don't worry about that from last time. let's start with this linear model. A feedforward neural network model is going to be very similar to a linear model, except that it's going to include some nonlinearities. Okay, and so let's start with an example. And the example is as follows. So here's a representation. Here is a symbolic, I guess, symbolic representation of this model. This model has, again, takes input x, but it has now double the number of parameters, right? So double the, at least in terms of symbols, double the number of symbols, right? So what are the symbols? There's going to be W1, B1, and W2, and B2. Okay. So previously there was only W and B, and we said, hey, the function is going to be like this, Wx plus B. This is it. Okay. Whereas now, here we are talking about an example of a feedforward neural network model. It's just going to have a nonlinearity. So if you look at it, first we're going to take x and do the same linear transformation that we were doing before, W1x plus B1. Okay, it's basically Wx plus B. But then we're going to do a nonlinear transformation. Okay, and that's given by max of 0, the second argument. Okay? And I'll talk about that in a second. Once we get some intermediate thing, let's call this z, for example, then the second transformation is also linear, W2 times z plus B2. Okay, so what do I mean? So let me just elaborate it one more time. So so this model has two pairs of parameters, W1 B1 and W2 B2. First, we're going to take input and multiply with basically a linear model, or just multiply with a matrix and add an offset vector. Okay, and let's call this z. Okay, this is going to be potentially a vector of some dimension, right? So, for example, if you recall the multi-class algebra regression, this would ideally have been a vector of size 3 if there are 3 classes. This z. Okay, but it doesn't matter. Some size of this vector. Okay. Now, next there's going to be a nonlinear transformation, which is max of 0, z, and we'll actually spend a few minutes on just understanding this nonlinear transformation. But for us, for now, let's just assume that there is a nonlinear transformation. Okay, we're going to just 2 slides. We're going to discuss why this is a nonlinear transformation. Okay, this is going to give me let's call it the output, and this is equal to z out. So some transformations happening. So I first did a linear transformation and then did a nonlinear transformation. I got z output. And then the third step is, hey, take the z output and multiply with the matrix W2 and add this offset or some offsetting matrix, offsetting vector B2. Okay, and that's my output. Okay, that's this F. You can just call it. I mean, if you want to use this previous terminology, you can just call it scores, okay, or score, some score vector. If it's a 3-class classification, it's going to be 3 cross 1, for example. So this is the extra step. So you can see that there is a nonlinearity here. And just to fix a few things, just like we did last time, x, let's say, is d-dimensional. So in our example script from towards the end of last session, d was equal to 2. Right, so we had a 2-dimensional data. So we plotted it, and today also we'll see the same plot again. It was 2-dimensional. So D is 2-dimensional. X is let's say 2-dimensional feature vector. Okay, so W1 is going to be because it multiplies with X. One of its dimensions has to be the same as the dimension of X. So it's 2 times some output dimension Q. So this is that output dimension Q. So this is going to be Q cross 1, because W1 is going to take, it's going to get multiplied with a X vector, which is 2-dimensional, but it's going to produce an intermediate vector, let's say Z, which is going to be some Q dimension. Q, let's say, is 10. Okay, so we get some 10-dimensional vector out. Okay? It's just a vector, matrix vector multiplication. You just need to align the dimensions and the output dimension. Sorry, once you multiply a matrix with a vector, you get another vector. Okay, and the dimension is appropriately chosen based on the dimensionality of the matrix, right? So let's say Q is 10. Okay, then this guy is going to be 10-dimensional. This nonlinear transformation here is also going to, turns out it also going to retain the dimensionality. So it's also going to give a 10-dimensional output, or whatever Q-dimensional output vector, Z output. And then since I'm multiplying a 10-dimensional vector here, W2 is one of the dimension of W2 has to be 10. So it in particular, since I'm talking about 3-class classification, W2 has to be 3 cross 10. Okay? because this takes a 10 cross 1 is essentially 10 cross 1, and this is 3 rows and 10 columns. So if you multiply, you get basically a 3-dimensional vector, and B2 also has to be 3 cross 1. Okay. So what I'm doing in this exercise is just to kind of get a sense of, hey, what's the dimensionality? And there's nothing hidden here. Okay, so everything is very clear. We do a linear transformation, we do a nonlinearity, we again do a linear transformation. In this 2-layer, it's called a 2-layer model, and we'll talk about layers in again a couple of seconds. So this is I'll talk about layers in a minute. Okay. So for this model, turns out this choice of Q tells you some sort of a sense of the number of hidden nodes. Okay, so let's actually write down things that I've not explained yet. So nonlinearity, in particular the nonlinearity max of 0, something z. So we'll talk about this in a minute. I'll also said layers. Okay, we'll talk about that in a minute. And second thing is number of hidden nodes, and what does hidden even mean? Okay, so here we are saying that here the number of hidden nodes is q, or whatever, 10. The number of labels is p, and we said, hey, if you're doing 3-class classification, you better produce 3 scores for each of the 3 classes. So the number of labels is going to be 3. Okay, and here I just have a point, but I'll talk about layer in 2 minutes. Okay, let me talk about nonlinearity first. Any questions at this point? I mean, we really transparently saw one example model of a neural network, actually, and it's called a feedforward neural network. Okay. I need to see the chat. Okay. Yeah, so there's a question. The scores are linear or non-linear transformation. So remember, the function has to return scores, right? So again, if you look at the def, so these are basically scores. Okay. In the previous example, in the linear model phase, you would get input x, you just do wx plus b. These are basically scores. Okay. And that's, I mean, just returning that. And so those are scores. Here, again, the scores are the same thing. Whatever scores are supposed to be 3-dimensional, again, if you're doing a 3-class classification. Now, the scores are not linear, so they're not linear in X, okay, because there was an intermediate nonlinear transformation. So X, there was a linear transformation. This was step 1. Step 2, there was a nonlinear transformation. Okay, so it's like saying, hey, from X I went to X square. That's not linear anymore. So because if you change X by 1 unit, X square doesn't change by 1 unit. It can change more or less depending on what the X value is. So it's not a linear transformation. For example, X square is not a linear transformation. So only like scalar multiples in 1 dimension, only scalar multiplications are linear transformations, right? And maybe plus offset. If you really talk about linear transformations, yeah, scalar multiples are linear transformations. Okay. So step 2 is making is kind of making the scores non-linear transformations. When I say non-linear transformations, non-linear functions of the input x. Okay. So remember, whenever we use the word transformation, it's the same as saying a function. Okay? So when I say linear transformation, it's a linear function. So the question here seems to be, are the scores, are they linear or nonlinear functions of x? Okay, and this was an example where the scores are not going to be linear functions of x. Okay? They are linear functions of x in the first case, but they're not in the second case. So let's talk about linearity and nonlinearity with this table. Okay, so what is this table showing? It's listing basically 3 columns. It has 3 columns and a bunch of entries in each row. So and the first column is just the name of nonlinearity, or name of a transformation, or a name of a function. Okay, it's all the same thing. Second column is just showing what is that transformation, or what is that function. Okay. Third column is when was it introduced in this neural network literature. Okay. And we'll spend some time on the 3 red, 3 things highlighted in this blue box. But you can see the first entry, there's no name for this transformation because this is not a nonlinear transformation. It's y is equal to x. It's a linear transformation. Or y is equal to 5x is also a linear transformation. Okay, so but the first critical fundamental thing that is used quite a bit in defining neural networks is nonlinearity. And so we look at 3 types of nonlinearity. These are the names: sigmoid, tanh, and ReLU. And these are some of the years when they were introduced or reintroduced into the literature. And in fact, by the way, this is equal to the same as max of 0, x. Okay, so we'll see what this function looks like. We'll see what this function looks like, and we'll also see what this function looks like. But you'll see in the previous example we use this. So we'll come to that in after looking at the first 2 examples. Let's start with sigmoid. So what is the transformation? So what is that nonlinearity or nonlinear function? Okay. So it's all one dimension. So for now, just just not worry about the neural networks part. Just focus on this function. It's a one-dimensional function. And here's a one-dimensional functions just mean it takes a number and outputs a number, basically, no vectors, no matrices, and all that. And here, and since it's a one-dimensional function, you can actually plot it. So you can plot it y is equal to f of x. Right? I can't use f, but okay, let me use f here. It's okay. So you can think of x as this x-axis here, and y is this y-axis, and this is the sigmoid function. So as you can see, there's a function which is like a step, basically, a smooth step. And you might have seen this earlier in when we're talking about BackProp. We had seen this function. Okay, in fact, we had seen this function. It was 1 by 1 plus e to the power minus b. Okay, so if you think of z as the input, sorry, I changed the function names here. So and g of c as the output, then this is the node. This is the computational node that you would see. Okay, so what is the specialty of using this function? So let's step back for a moment. When we had this function x is equal to wx plus b, this function would on the computer, would be actually mapped to this a computational graph. Okay, so if you remember that we had tried out very simple computational graphs in the last lecture. So this function, okay, sorry, this is not x here, so let's call it scores, okay, some s thing. So you basically have a computational graph where you start with x and w and b, and x and w are like this is a matrix vector product. You'll get something in between. You'll take b, and you'll get s in the basically this is an addition operation, and you'll get an s. Okay, these are all vector operations, but b is going to be 3 cross 1 in a running example. So similarly, you can imagine if there is a with the function that we had, if you're going to have some nonlinearity, so this is going to take z as an input and produce d of z as an output. Okay, and you'll see that we're going to use something like this in the neural network, right? We already saw max of 0 comma something as one of the nonlinearities. So let's say we had this g of z as a nonlinearity. Then it will also be a node in some computational graph. Okay, so because you have to represent it as a computational graph on the computer. If it's going to be a node in the computational graph, then if there's going to be some, we have to, again, any model that we have to figure out the best parameters so as to minimize some sort of a loss value on the training data, right? So figuring out those best parameters requires computing gradients generally, because we are actually looking at functions which are differentiable, as I said. And if you want to look at gradients, then we know once we have a computational graph, we only have to look at, hey, incoming gradient times the local gradient, we just pass it back, right? So we have seen this before. And so if you have this type of nonlinearity, this blue node here, then whatever the incoming gradient, whatever it is, we don't have to worry about that number, okay? Times the local gradient. The local gradient is going to be gradient of g with respect to gradient of z. Okay, I'll just multiply the incoming gradient with the local gradient, and that's what I will pass back. Okay. Now, the key thing about this nonlinearity, the example nonlinearity that we picked, sigmoid nonlinearity, okay, whose output, by the way, is only between 0 and 1. Okay, it's positive. It's only between 0 and 1. So whatever value, whatever input value you pick, all the way, let's say minus 100 or minus 1000, it's never going to go below 0. And even if you pick, let's say, 1,000,000 as an input, as an input number, it's never going to go above 1. Okay, so that function has a saturation property. Okay, what do we mean by that? You can see that at this region, if I change, let's say, z value from 4 to 6, you can see that the function has not changed much. Okay, which means that the gradient is actually very close to 0, because you can see, hey, I changed from 4 to 6. That was 2 units of change in the input, and the output maybe changed from 0.99 to 0.999. Okay, that's a very small change. Okay. Similarly, you can see that when v is varying from -4 to -6, again, the change here on the y direction, as on the y-axis, is minuscule. Okay, in fact, it's overshadowed by my highlighting there. And you can, it's going to be even more severe, if you go from, let's say, -60 to -100. Okay, although 40 units change in terms of input, the output doesn't change much. Okay, so in some sense, since the output doesn't change, the local gradient here in this region, let's say, gradient of g with respect to gradient of z, is going to be very close to 0. Similarly here, okay, same thing here, gradient. Very close to 0. Okay. And if I multiply with a number which is very close to 0 times anything that's coming in, it's gonna get squished, right? It's gonna be like almost 0. Okay, so that is a characteristic of this function, this nonlinearity. But you'll see that people will still use this nonlinearity in defining different types of neural networks. But this is one characteristic. It may be a good thing. It actually may be a bad thing. Second thing is the function itself is not zero-centered. Okay? So the numbers get shifted, right? So like whatever is the input, let's say that the input was, is evenly distributed between positive numbers and negative numbers. But the moment, the output is going to be all between zeros and ones. It's not, there's no negative numbers. Okay, so it's some sort of a shift happening once you apply this transformation or this function when you're trying to compute your model's outputs. Okay, so those are two characteristics of this particular function. Any questions at this point?
Professor, could you please repeat the last point?
Yeah. So we already saw that this function g of z, if you take numbers, let's say, and this is just illustrating the same thing. So if you take numbers -4, -6, -4, -2, 0, all the way to 6, if I transform them, I get numbers from, let's say, 0, almost 0.1, let's say, to 1.1.5, all the way to, let's say, 0.9 or something. So you get numbers which are not negative. So that's what I mean by, so if you take the mean here, it's not 0, right? It's not 0. But if you take the mean here of these numbers, let's say it is, take the sum and divide by whatever number of numbers there are, I mean, it's equal to 0. Okay, that's what I meant. It's not zero-centered. One way to easily fix this is to say, hey, why don't you subtract g of z minus 1/2? Okay. If I do that, then it seems like this function is symmetric, right? So what do I mean by that? So let's say, think of this function, which goes like this. Same function. Okay, in fact, the definition of the function is going to be g of z is equal to 1 by 1 plus e to the power minus z minus 1 by 2. Okay, this function, z is this axis and g of z is this axis, goes through 0, then it's going to be 0. And for high values and low values, it's going to be whatever. So it's going to be 1/2 highest value and 1/2 minus 1/2 the lowest value. This is a zero-centered function. That's all I meant.
Got it.
Yeah.
Yes, clear. Thank you.
So these are just a couple of properties that I'm highlighting only because I want to differentiate between 2 or 3 nonlinearities. And we'll stick with one of the nonlinearities probably for the much of this session. But I just wanted to point this one out because we're going to pick this type of nonlinearity a little bit later in some other class of models. So today we're only looking at feed-forward networks and convolutional networks. Any nonlinearity, so by the way, any nonlinearity in this table, or not just in this table, you can pick any nonlinearity you want. and they're all valid nonlinearities to use in your model definition. So you can say, hey, I want to use a model which has more nonlinearity, which is basically like say this row. Okay, that's fine. So that's a definition of your model. So the question is, why are you choosing that model versus some other nonlinearity? That comes down to maybe empirical performance of some nonlinearities or some other nonlinearities may be easier to train your model, in a sense, doing gradient descent and so on. Okay. And so, for example, the sigmoid, because of saturation effect, may or may not help training, because if the numbers are, if inputs are, way high or way low, then the local gradient, really kills the incoming gradient. So there's no gradient update, right? I mean, recall the gradient update. There was this W new is equal to W old minus, let's say, 0.1 times the gradient of the loss with respect to, let's say, W. So when computing this, if this thing is, ends up being 0 because the nonlinearity is such that, it's a sigmoid nonlinearity, and it multiplied whatever the incoming gradient was with almost a number which is close to 0. If this becomes 0, then W old is almost the same as W new. So you don't really get a new set of parameters. Okay. But I mean, we will keep revisiting these ideas again and again. So let's move on to another example of a nonlinearity. Okay? Just as a visualization, that the second nonlinearity is called tanh nonlinearity. Okay, so it's the hyperbolic tan function. Okay, and there's a formula, but let's not focus on the formula of this function at all. It takes, again, some input z and produces some, again, some number, scalar number, one-dimensional number output. And this is a figure from, I believe from Wikipedia. So here's the function. So this function is this dashed line. Okay? And this function, you can see when input is 0, the output is 0. Okay? And it also is such that when input is large, it goes up to 1. So you can see this is up to 1. And if the input is really small, it goes up to -1. So it somehow squishes the input. Okay, so squishes the input in the sense that if the input is -100, the output is going to be very close to -1. Right? If, let's say here it's -100, then the output is very close to -1. Okay, so tanh is another. It's very similar to the sigmoid function, but the expression is going to be different. The functional, expression is going to be different. And some folks, and it was being used, okay, in some early versions of neural networks that were being studied. It was used, and we'll see we'll see it being used in another popular neural network, maybe a couple of lectures from now, okay, called recurrent neural networks. But I don't want to jump up to that point. But here is an example of something which, at least doesn't have the zero centering issue. Okay? I mean, in the sense that by definition, it centers things around 0. And the gradients still vanish in the sense that, if the input is too large or too small, too negative or too positive, and then the local gradient happens to be 0. And so if there's an incoming gradient, even if there's some signal, it just gets multiplied with basically 0. Okay, while passing it back in the computation graph. Now let's look at the third nonlinearity, which is exactly what we saw in the first example. It's called the ReLU nonlinearity. Okay, it was reintroduced in 2012, or basically introduced into this deep learning literature around this time. And the function is, did I not write the function here? And the function is basically, split in here. Inside the circle, it's max of 0, z. Okay? So z is an input, and the output is going to be max of 0, z. Okay. And ReLU is happens to be a short form for rectified linear unit. The naming is not very critical. You should just know that this is the function that we're talking about. Okay? Max of 0, z. And let's look at the function. How does it look like? So this is the function. So this blue curve is that function. Okay, max of 0, z, or max of 0, x. And so this is I guess here it's labeled as rectifier, but just call it as ReLU. So what does it do? If the input is a negative number, then the output is 0. So on this is max of, let's say, 0 comma x in this graph. So if x is negative, then max of 0 and a negative number is going to be 0, right? So I'll always output 0. If x is positive, then max of 0 comma that positive number is going to be that positive number. So I'm going to output that positive number. So on the positive side, it's just a line. Okay, it's all one-dimensional plots here. It's just a line with 45 degrees. Okay. The slope is 1, or basically y is equal to x. Okay. If x is positive. If x is negative, then it's 0. Okay. Now this function, oh, by the way, looking at this plots, you should be able to say that this is not a linear function. And that's because it's input is not, if I change input linearly, output is not changing linearly. Okay, for example, when I change input from -2 to -1, the output is not changing at all if in this range. But if on this side it's linear, okay, on when x is positive it's linear, when x is negative it's not linear, it's actually constant. Similarly, same thing on this side. This is a nonlinear function, the dashed one. Okay, let's focus on the dashed line here, the blue line. Because input is, if I change input by 1 unit or 10 units, the output is not changing by 1 or 10 units, okay? or proportionally, basically. Okay. So this is the third example of nonlinearity that we are seeing right now. And one of the key reasons I would say that we are looking at it right now is happens to be that empirically, the models that use this nonlinearity in their model definition happen to do well in terms of the prediction problem at hand. If you're doing a classification or if you're doing a regression problem, if you define a neural network with neural network will have some nonlinearities in there. If you use this nonlinearity, it turns out that somehow the functions are able to fit the data better and able to have good test error and so on. Okay? That's the number one reason. Even the other nonlinearities are good, but this one seems to be pretty versatile. Is features in multiple different, I guess, classes of deep neural networks. Okay. But it also has issues. So for example, the gradient here is exactly 1, right? The rate of change of the output with respect to input when x is positive is just 1. So it just, whatever the gradient is, whatever the incoming gradient is, this, as I said, is equal to 1 if z happens to be positive. Okay, if z happens to be positive, just whatever I got in, I just pass it to the predecessor node in my computation graph. Whereas if z happens to be negative, then no, I don't, whatever gradient I get as input, I ignore it and just pass, send back 0 because this guy is actually equal to 0. Okay. So on the positive side, gradients, whatever the gradients are, just pass it back. So gradients don't get multiplied with 0, which was the case, right? In sigmoid, if input was like really large positive number, in the sigmoid case or the tanh case, the gradient would be like basically 0. The gradient which is passed back to the predecessor nodes would be 0. But here it's not the case. But it also has some other issues. For example, because on certain direction, on this side of the curve, the local gradient is 0. So if it happens that your parameters and your training data numbers, the numbers in your training data are all such that z happens to be negative, then you'll basically there'll be no gradient information passed on. Okay, so it's some sort of a gradient stop. So in that sense, it's called a gradient gate. So any questions about up to this point? We just saw 3 examples, and now we'll come back to that feed-forward neural network representation that we saw earlier. Okay, which the 2 pairs of parameters W1 B1 W2 B2. We'll now start using figures, okay, diagrams to now delve deep into the expression. Instead of looking at function expressions like just the symbols, we'll draw diagrams for the neural networks, okay? And that will give us a layer view, hidden nodes, hidden layers, nonlinearities all become a little bit more apparent. Okay, so let's actually move forward. So the previously we saw this function, okay, the function at the bottom. Okay, as an example of a feed-forward neural network. Okay, so as I said, it had 2 pairs of parameters, and this was the functional form. So what we can do is draw this function. Okay, draw this function, and
Professor,
yeah.
can I interrupt you? Sorry.
Yeah.
I have a question regarding the functions before ReLU, tanh, and sigmoid. What if the input is 0, and how does it perform?
Yeah, so if max of 0, 0 is 0. So
0, yes.
yeah, the function evaluation itself could be something. Okay, so if you evaluate the function at 0 for, let's say, tanh, it's going to be 0. And for sigmoid, it's going to be 1/2, right? E to the power 1 by 1 plus e to the power minus z. E to the power 0 is 1. So 1 by 1 plus 1 is 1/2. Okay. So function evaluations are some, 1/2 and 0 respectively. But the slope, depends. So slope here is actually, I mean, you'll have to look at what is the derivative and then tell the slope. But maybe it's 45, I think. I don't know exactly. So maybe it's 1. I don't know. But slope for sigmoid at that input value 0 is going to be some non-zero number, some slope. Okay. Same thing with this tanh thing. But for nonlinearity, there is no derivative defined at 0. Okay, because it's unclear what the derivative is. Okay, here.
Okay, got it.
It's not differentiable, this function, at that point only.
Okay.
So what do people do? I haven't paid too much attention. So there are many things people can do here. Okay, we can pick one of the slope values as a candidate slope value. There's going to be many slopes at this 0 value.
Okay.
So let's not get into that at this point. Yeah.
Thank you.
Yeah. So now let's deconstruct some of the terminology that we have been using. So we'll have a pictorial diagram for this function as shown in this figure. Okay. And here I've just assumed a few things. So I've assumed Q to be equal to 4. Remember, Q was the dimension of this matrix here, one of the dimensions of the matrix here. Input, I've assumed 3 dimensions. Okay, 3-dimensional input. And output I assume to be 2 dimensions. So it's like something like a 2-class classifier or a regression with 2 target variables. So this is a diagram of this function. We're trying to represent this function. So there's going to be an input layer. There's going to be a hidden layer, and there's going to be an output layer. So how does this expression map to this diagram is a natural question here. And the way it maps is as follows. So W1 x plus b. So this W1 and B1 are related to these edges, the first set of edges, W1 and B1. Okay, the black ones. And then W2 and B2 are related to the second set of black edges that you're seeing. Okay, so if you see 2 sets of black edges, you just naturally just think of, hey, there are 2 sets of parameter pairs, W1 B1, W2 B2. And so what else needs to be said is, hey, there's a nonlinear max of 0, something going on that goes on in each of these nodes here. Okay, so this figure is not exactly a computational graph. Okay? It mimics, it resembles a computational graph. Remember the computational graph from last time? For even a small function, we just explicitly wrote the graph. Hey, here's an addition node, here's a multiplication node, here's some other transformation node. Here, it's not exactly the same. Okay, it's the objective of this diagram is not to exactly say what the computational graph is. The objective of this diagram is to just get a sense of a layered view of neural networks. Okay, and feed-forward neural networks are first set of neural networks that we're looking at, and they can be easily thought about in terms of like layers. Okay, and so that's what we're trying to attempt here. Okay? So we have 3 layers: input, hidden, and output. Okay, so what hidden is any layer which is not input or output, basically. It says it's a 2-layer network, although you can say there are like 3 names for the layers. Just think of it as, we don't really consider, let's say, the input layer as a layer. Okay? So just think of hidden layer and output layer. So I mean, in terms of counting, so that's why it's called a 2-layer neural network or 1 hidden layer neural network. So because there's only 1 hidden layer, 2 layers because just represent the 2 sets of parameters are basically the hidden layer and an output layer. Now we'll spend some time on what is a node in this diagram. So because this orange circle is unclear what this orange circles are. For at least for input, it's clear. If my input is 3 dimensions, 1 circle for each of the x1, x2, x3, the 3 coordinates of my input, okay, of my input feature vector. But this the second set of orange. And actually this at the output side, just think of the score 1, score 2. Okay, the 2 score. Think of 2 class classification. There's only 2 scores, score 1, score 2. So so output is just those 2 numbers. Okay. We'll talk about node in a little bit more detail in the next couple of slides. Okay. And we'll also talk about, and the node basically also contains the nonlinearity. And the nonlinearity is also called as an activation function. So a little bit of terminology here. The nonlinearity, this max of 0, input, second argument, whatever it is also called an activation function. Okay. So it's just recap. We have now mapped this function here, f of x comma w1 b1 pair, w2 b2 pair, into this diagram, representative diagram here, just to get a sense of layers. Okay. And so what I'm trying to say, and the important thing is this w1 b1 and w2 b2, they are like, as I said, they are related to edges, and you can think of this edges as basically a part of a layer, right? So it's like, hey, first set of edges, first set of parameters doing something, and then the next second set of parameters doing something. So those two are like 2 layers or 2 layers of computation. Okay. Yeah. So I mean, and so typically what people do is, hey, what's the number of layers? Sorry, what's the number of layers in this feedforward neural network? In any feedforward neural network, it's just going to be the number of pairs of w comma b's. Okay. And by the way, why am I explicitly writing these pairs? There's just a linear transformation, right? So so if you give me an input, I'll just do wx plus b. If you give me some other vector z, I'll just do wz plus b. For any pair of w comma v, I can just do this, and that's like that's like a layer level computation that I'm doing. Okay. And so this is exactly what's happening. So let's say some bunch of inputs, they get, as I said, here there's going to be, let's say, w1 b1, and here there's going to be w2 b2, and these are just outputs. Score 1, score 2, score 3, score 4. If it's a 4-class classification, I think in the previous picture there are only 2 outputs. So let's drop this, and let's also drop this. So this is what we were seeing in the previous diagram. In turned, which was horizontal, here is a vertical representation. Okay. And even at this point, you can say, hey, this function, you just told me there's a pair of parameters, w1, b1, w2, b2, and you saw that some dimensions are kind of constrained. Like if input is 3 dimensions, then one of the matrix dimensions has to be w1's size has to be 3 dimensions, right? So let me write it here. If it's w1 x plus b1, if this is 3 dimensions, then w1's one of the dimensions has to be 3, right? But I think in the few slides ago, I said the second dimension, let's pick it as 10. Okay, or in this example, actually, let's mirror this example here. We can use 4. Okay, because there are 4 nodes here. I hope there are 4 nodes there. Yeah. So let's say w1's number of rows is 4. We get to choose this. Okay, and the number of rows that we pick for w1 is going to be the number of hidden nodes or the number of neurons of the hidden layer. There's one hidden layer. The number of neurons in this hidden layer is 4, or the number of nodes, neurons is the same thing, is equal to 4. Okay, just and what does it correspond to? It also corresponds to the number of rows of the first weight matrix or the first matrix w1. Okay. So that's one choice that we can make. And the second thing is, hey, why did we only pick one hidden layer? Can we do 2 hidden layers? That's going to be a different function. Okay, but we can, nobody's preventing us from doing that, right? So we can do first. So that function will look like, hey, let's do w1 x plus b, B1. Sorry, and then let's apply a nonlinearity. So let's say 0 and max. Then let's do W2 times whatever is output plus B2. This was a function that we are talking about. But nobody's preventing us from doing this, right? 0 and this max, and then doing a W3 plus B3. Okay. Now this very complicated, very not complicated, but too expressive of a definite, function definition. Now, this actually corresponds to 2 hidden layers. Now, but once you look at the figure, you can ask, intuitively ask this question of why one hidden layer, why not more than one hidden layer? Why not, why only have 4, for example, 4 hidden units or 4 neurons or 4 nodes in the hidden layer? Why not more? Because output is an NA fixed. If it's a 2-class classification, there only has to be 2 outputs. Input is fixed. I mean, unless you do some extra feature engineering, introduce some transformed coordinates, that's up to you, but that's kind of fixed. What you can change is the number of layers and nonlinearities associated with the layer. Okay, as well as the number of layers, nonlinearity associated with the layers, as well as the number of units in each layer. Those are things that you could potentially change. Okay. And the question is, how do we choose this? And the short answer is there is no one true way or one optimal way to do this. This is just dependent on which class of models or what choices are getting you a good validation error or a good like out of sample error. So is the function like a pictorial representation of the feedforward neural network function, the model function, clear?
Professor, this might be a silly question. I did not understand one thing. If W has 4 cross 3, it differs the number of layers or number of nodes.
Number of nodes in the one hidden layer that we have. Okay.
Okay.
So this 4 I just chose because there are 4 green knobs here, as well as there are 4, like whatever green knobs or whatever those nodes in the hidden layer here.
Okay. And how do we change the layers then?
Yeah, the number of layers. If you change the number of layers, the picture is not going to be this picture. Okay, it's going to be. So let's say this is 2 hidden layers, then you'll have, let's say 3. Bunch of that are, I don't want to draw those edges, but bunch of edges. Let's say the first set of nodes, first hidden layer has 4 nodes. Okay, and then I can have bunch of edges, and I can have 5 nodes, and then I can come back to those 2 nodes.
So how will the equation change? How will the equation change?
Yeah, this is the equation. This is f of x, w1 b1, w2 b2, w3 b3.
Okay.
It's an example equation. Okay, so this is not the only way to have a two-layer hidden layer, because I've used a specific nonlinearity max of 0, something. If you use, let's say, sigmoid, the expression will look a little bit different, right? Instead of max, it will be, hey, sigmoid of whatever is the input. Okay. I've used 2 nonlinearities here, corresponding to each of the 2 hidden layers. So think of it this way: this part is related to the first set of edges.
Okay.
This part, and then this this part.
Second set of edges.
Yes, second set of edges. And then the whole thing in the box is basically this
for the third. Okay. Got it.
Okay. It's 3 layers, but 2 hidden layers.
Yes, understood. Thank you, Professor.
Yeah. Professor, I have a quick question. What is the reason we use more than 1 layer of the hidden layer? Like, I mean, right here we're using 2 hidden layer, right? Yeah. So how is that going to change our outcome? How does this benefit our outcome?
Yeah. So why use 1 hidden layer, 2 hidden layer, or any number of hidden layers? That's a choice that we need to make. How to pick the number of layers. Okay. The more number of layers you use intuitively gives you much more complicated nonlinear functions. Okay, because remember, linear function is something like this, right? So a linear function is basically exactly like this. if you add an intercept, it may be shifted. But let's say this is an example of a nonlinear function, right? This is a quadratic function. This is not nonlinear enough. What if you wanted, even in one dimensions, what if you wanted a function like this? For some x values, it has to be close to 0. Some other x values are high, and so on. So this messy function, okay, you can probably use polynomials here, by the way, as for x versus y. But basically, the more nonlinearities you use, you can actually get many nonlinear functions like this. I'm only illustrating in one dimension, but in higher dimensions, this is what you can do.
Okay, gotcha. Thank you.
Yeah. Yeah, actually there is, so people, mathematicians have figured out that, hey, even with just one nonlinearity, you can approximate any function. Okay. So whatever function, let's say I give you a sinusoid, let's say, you can actually just use a one hidden layer neural network to approximate this. Okay, it's called the universal approximation theorem. But anyway, that's not important for us. What I'm trying to say is that the number of layers, the number of nodes in the layer, all those are up for grabs in the sense that we need to figure them out as just like a hyperparameter choice in our application. Okay, and you'll see that for images or for text, there are big models being built by big tech companies and research labs. Those guys have figured out some choices. Okay, like, hey, we need to have 10 layers of this and 2 layers of that, and there should be 1,000 neurons in each layer. They have experimented and they found some choices for which they are able to really do good image classification, for example, or do text generation, for example, and things like that. So we'll just have to go with their choices. But at the end of the day, all these choices are going to be empirical. It's going to be really application driven. Yeah, so let me not talk about backprop, because backprop is the same idea. Once you have a computational graph of this function of any neural network, at the end of the day, the neural network is just a function. It given an input has to produce an output, just like a random forest function or a SVM function or anything like that, or linear function. So once you have a computational graph, and typically, as I think I mentioned it earlier, and this is not something that we saw in the code last time, but you basically generally do batch-based training, batch gradient descent. Okay, so you, instead of looking at a loss over all training data, you generally look at loss over a small set of training data in every iteration, every update of your weights. Okay, and the rest of the idea is the same. Okay, so basically get the gradients with respect to parameters. Now there's a little bit of an explosion in the parameters. Now there's twice the number of sets of parameters, right? It's not just W1, B1, but also W2, B2. But the same idea applies. Once you have a computational graph, it's all mechanical at that point. Okay, there's no intuition or any big insight to be gained there. But in the last lecture, we just wanted to get a sense of, hey, what are the parameters? How does the computer know how to work with these? How to do gradient descent, right? How does the computer know how to do gradient descent? And that's where we saw backprop and stuff like that. Okay. And so let me skip that. So at this point, let me jump over to Google Colab, and let's look at yeah. Let's look at I want to move this. Wow, I can't even move this. Somewhere. Let's do it this way. Okay, so I hope the screen size is not shrunk too much. Oh wow, it became same position again. Okay, it's fine. Quick Google Drive. I don't know if no. Let's go back to maybe recent. No. Okay, let's actually go to Drive. Okay. Text decoder, I think I have an issue here. Okay, that's, I guess, the issue of using Internet Explorer, maybe. So what happened?
If you have Chrome,
Yeah, I mean, this is just a new installation, so I don't have Chrome. Okay, let me install things right now. Okay, let me just get Chrome. Oh, I'm out of share. I'm not sharing my screen. That's not correct. Let me install Chrome. Give me a second. Sorry, in the meantime, if you have any questions, I'm just installing Chrome right now.
Oh, sorry, is there any specific reason you are using Windows today?
No, I just had to I had to get a Windows environment for helping out some students in a different class in MLOps. So just a change of faith, I guess. Okay, it's pretty much installed. Asking me to sign in and all that, but that's okay. Let me just go to Drive. Go to Drive. Sorry, I'll just share in just 1 second. Okay, great. So I do see the Chrome is working. So let's get to Chrome. Google Chrome. Yeah. Okay. So sorry about that hiccup. FeedForward classifier. Open. Okay. So actually, this notebook is going to be very similar to the previous notebook, and I don't want to spend too much time on the explaining the code right now. Let's see if we have some bandwidth to come back to this code at the end, if in terms of explanation. But you will look at this code for the second half of your assignment. So I'm sure there's going to be opportunities for us to discuss this code offline. So let me execute this just to get I want to show you that, hey, the issue that we saw with linear model on the simple 2D data, that's fixed, for example, using this model. Okay. So sorry, this feed-forward neural network that we're gonna see now. In particular, I mean, I'm just here. Second cell is just running the data, getting the data. So this is the data actually. So this figure here is the 3 sets of data: the yellow, the red, and blue or purple. Now here's the feed-forward neural network. Okay, so instead of W1, B1, we just chose W, B, but it's just W1, B1, and there's a W2, B2. Okay, so that's just double the parameters that we saw from last time. And there's some choices, like here's 100, instead of that 4, for example, in our slide, or 10 or something, here it's just chosen to be 100. Okay, why 100 and why not 1000? That's a great question for which there's no, I guess, immediate answer. Okay. Good. And now next, it's a very similar format to the previous linear model code. So there's going to be, for example, computation of class probabilities, basically the forward functions. For example, np.max, which is that nonlinearity of 0, x times w, or wx plus b. And then that's going to be a hidden layer. And since there's only one hidden layer, and then the hidden layer is going to get multiplied with W2, and then again B2 is added. So instead of two hidden layers, there's one hidden layer. So there's just one nonlinearity extra and one more linear transformation happening, okay, to get to scores. So let's run this, and let's not worry about all the gradient derivation here. But the idea is very similar. So you get to log prop, get the definition of your loss function, which is going to be exactly very similar to the logistic, the linear model or the multi-class logistic regression that we did. And I have mentioned that this before, but this loss function is also called the cross entropy loss function. Okay? And it's kind of very popular in classification problems. Whenever you pick neural networks, deep neural networks, you tend to use this loss function, okay, cross entropy loss function. Okay, there's some number of iterations that happened. So those many times we updated, okay, those many times we updated each of these four, W1, B1, W2, B2 parameters, or WB, W2, B2 parameters. We updated 10,000 times. Okay, why does it have to be 10,000? Why not 1,000? That's also a good question. That can come up. And a priori, it's unclear when to stop. And in fact, there are some heuristics like, hey, let's actually look at the plot of the loss function as a function of these iterations, and maybe at some point, maybe the plot of the loss over some held out validation data, maybe it stabilizes at some point, and then you stop. So we ran this. Now, as a cheat here, we are just using the test data to be the same as training data, so it's actually not representative of performance actually. And so it says, hey, accuracy is 0.98. So it's actually the training accuracy which we are reporting here. And then and actually the figure is already there. If you look at the plot, you can see that you are able to pretty much perfectly classify the purples, the reds, and the yellows. Okay. So this is in contrast to what we saw for the linear model, where it was cutting through, right? So that was the restriction. Linear models have to have linear decision boundaries, and for this data, you cannot have linear decision boundaries. If you can't have a line and ensure that the yellow region is exactly is separated from the, let's say, the blue or the purple and the red region. Okay, so try to play with this code. It's available on our GitHub notebooks link under examples, and you'll have to also potentially work through this. Those who have not yet started the assignment, you will kind of spend some time on this as you work on your assignment for next week. Okay. Yeah, and the second resource that I wanted to quickly point out, and that's also actually great if you even before looking at the code, you can use playground.tensorflow.org. And here is so it says here 2 hidden layers. So let's actually draw one of the hidden layers. One hidden layer neural network. Okay, so this is actually in the browser. It's a great I guess JavaScript based and demo that folks at TensorFlow have set up to get a feel for different things. Okay, so for example, here there are 2 features, x1, x2, 4 neurons or 4 hidden nodes. Okay, 1 hidden layer, and there's a output. Okay, here the output is it's a classification problem. So you just need to classify into 2 classes. Okay, so it's blue versus oranges or blue versus reds, and so the output is you can think of one output or 2 output, because if one for 2 class case, it's a little bit of a special case, because if one score is high, you can think of the other score is low, basically. So so let's not worry about the output dimension, but canonically it should be 2 dimensions. Okay, score 1, score 2, and whichever is the highest is the class. And here you can see there's a batch size aspect that they have, and how much test train data split you want. Maybe have 2 classes be this way, where there's a orange and a blue, it's different data set basically. And you can actually run training. Okay, so if I run training, you can already see it's immediately figured out. You don't even have to do. So these epochs basically are the updates on the weights. Okay, so it says 4 and 4. It's the update on the weight. So it has changed now. You can reset the network, and so now the decision boundary is unclear, right? It's cutting through everything. But if you run it, you can see the addition boundary is over here. And for this class, actually, you don't even need a hidden layer. You can actually remove the hidden layer, and this is basically logistic regression. So what the logistic regression that we saw last time, the code, this is exactly that. Okay, so you will always get linear addition boundaries. So let's pick, let's say swirl. So you can see this is the type of thing that we saw last time with our 3 classes, right? We have a linear addition boundary. It cannot separate the oranges from the blues. Any questions about this part? And you can choose also things like, hey, how much regularization, L2 regularization, for example, that's not in a code. Activation, there's no hidden layer, so activation doesn't matter. But if we added one hidden layer and keep 4 neurons, and here we saw earlier, we can have sigmoid, tanh, relu. It's exactly the same. Learning rate is exactly those parameters that we update right here. Learning rate is the step size here. So most of these parameters and most of the things here should make sense. I strongly encourage everybody to play around with this to get a feel for, hey, what is the dimension? What's the, I can add a lot of hidden neural networks, hidden layers, right? Okay, and let's say I train here, it's struggling to train. Okay, so let's see. Let's that doesn't matter. Maybe eventually it'll figure out. Okay, actually it's still training. Doing something. You can see how it's figuring out some trend. So this is addition boundary, which gives us better and better loss value on the training data, or yeah, on the training data. The training loss is 0.3, it's decreasing. Test loss is not changing much, but training losses seems to be decreasing. So it may eventually figure out it's probably stuck at that point. Okay, any questions at this point?
Hi, Teja. Is there a way that we can apply this website to the different assignments that we might have in class?
Unfortunately, no. But actually, the assignments. So let's talk about assignment 1, right? Assignment 1 is the only one which is relevant to this, because other assignments are talking about other networks which are not captured here. For assignment 1, there are easier ways to do it. Okay, so there's easier ways to do some of the questions. The easier ways are to not look at the code base, the explicit for loop and all that I gave, but just to use something like Keras. Okay? Keras is a choice that you can use with TensorFlow to simply define your neural network, like in 2-3 lines, and then simply call .train. So that you basically have like 3-4 function calls and it'll train your model. That would be the simplest, closest thing. There may actually be GUI-based neural network training products, but I am not aware. I mean, I don't remember any at the top of my head. But to get intuition, I would say, try these, this is useful. Actually, as I said, if you drop all these hidden layers, they should exactly do the same thing as what, not this one. This has one hidden layer. Okay, let's keep, one hidden layer. So this one actually should be the same as this. Okay. The only problem is the data set that I've used in the code that I gave you is slightly different. Okay, it's not these 2 swirls, but it's actually 3 swirls, 3 class classification. But you can change it and see that they should basically do the same thing.
Professor, I had a quick question. In the and sorry if you specify this in the assignment, but are we only using fully connected neurons?
Yeah. So I think for assignment 1, we are only talking about feed-forward neural networks. Yes.
Okay.
At most.
Right.
I think in assignment 2 onwards, assignment 2 will have convolutional neural networks, and assignment 3 may have recurrent neural networks and so on. Yeah.
All right. Yeah. Thanks.
Okay. So I wanted to show this, and okay. So actually, let's take a break for 10 minutes and resume at 7:32. And we'll switch over to a second class of models. And we'll have to compare and contrast with feed-forward neural networks, so it will become more cemented what feed-forward ones are. And we'll look at convolutional neural networks, okay, the next class of models. let's assume at 7:32. Okay, let's resume. And again, before I pick up the second topic, which is convolutional neural networks, I strongly encourage everyone to ask questions. There is no wrong question here. And if you think you have a question, probably other folks also have the same question. So it's okay to ask a question. If it does take a long time, I can defer it to maybe later on and so on. So do ask questions whenever needed, and don't stop, because otherwise you may not follow the next few minutes after the session. Okay, so that's okay. So what we're going to do, so far what we've seen is feedforward neural networks, and there's not much more to it. Okay, so basically we saw nonlinearity and a layered view. And what I'm going to do is spend a little bit more time on layered view because it'll help clarify a little bit more about feedforward neural networks. So although we're going to start talking about convolutional neural networks, we'll spend a little bit more time on layered view again. And once you have these two ideas, layered view are therefore hidden layers. Feedforward neural networks are just just choosing the number of hidden layers. Okay, so let's say you choose 10 hidden layers and some bunch of nonlinearities, maybe the same ReLU nonlinearity, or you can even change the nonlinearities if you want. And that's it, some input to output mapping with a bunch of hidden layers. Okay. And you will notice that these are going to be called fully connected layers. Okay, fully connected layers when I'm going to contrast them with convolutional neural networks, convolution layers. So let me. This is a. We're gonna look at this name again. So we'll touch this again. So CNNs. So these are going to be very similar to feedforward neural networks. So, but there's certainly going to be some difference because they have a different name. Where what is special about so what's one characteristic of feedforward neural networks is that we could represent them as those diagrams, right? Those layered diagrams. And in those layered diagrams, at the layer we had a notion of a node. Okay, a node is also called a neuron. And what's new, which I did not present earlier, okay, in the slide, is that each node is going to be is associated with a bunch of weights and a bias. Okay. So I think I have a figure. Yeah, I have a figure in the next slide. So let me not draw another figure here. So I want to spend a minute on this. So each node in the previous layer diagram, I did not even specify like what computation is happening. I said only thing I said earlier was that it was not exactly the picture was not exactly a computational graph. Okay, but the picture was useful for us because we can see, hey, there are going to be let's say 2 layers, 1 hidden layer, number of nodes in a layer, for example. It is just useful for us to intuit about this class of models. Okay, this class of neural feedforward neural networks. Okay. So now I'm saying that each node is associated with a bunch of weights and a bias. Okay. Now, what we know from the expression was that there was this something called, we had used these, W2, B2 as a set of parameters for that one hidden layer neural network. Okay. So what I'm going to do in the next couple of minutes is just relate to, what is the weights and bias associated with a single node and this set of parameters. Okay. Actually, these are called weights and these are called biases, but there's going to be some weights associated with certain nodes. So for each node, there's going to be only some weights that are going to be associated with it, and only some parts of the bias, parameters also going to be associated with it. So we're going to talk about that. Okay. In particular, this node point of view, okay, this node, I did say that it's different from a computational graph, but at the same time, there's some similarity with a computational graph in the sense that this node receives an input, okay, and receives an input and performs within that node essentially the following happens: a dot product of two vectors happens. There's basically two vectors that it will get. It'll multiply those two vectors coordinate wise. That's what a dot product is, and we'll see an example in a minute. And then it also applies a nonlinearity. So if you think of a node, it's basically getting two things. One, let's say some vector 1 and some vector 2, and I'll map it back to what vectors are. Okay, these are going to be something related to these guys as well as data, but we'll talk about it in a minute. And then what it'll do is, hey, can I compute? Let's say vector 1 is vector 1 is, let's say, 1, 3, and vector 2 is 4, 5. Then it's going to do a dot product. A dot product is nothing but pick each coordinate, multiply them, 1 times 4 plus 3 times 5, and then sum them together. So it's 19. Okay, and then this number is going to be passed through a nonlinearity. Okay, so nonlinearity, let's say max of 0, 19. Okay, and that we know what that is. That's just exactly equal to that. That's the output here. Okay, so that's what this node or a neuron does. Okay, it just multiplies a bunch of, it multiplies two vectors and then applies nonlinearity, and it may optionally also add a bias. In fact, it'll add a bias. So actually, the third thing is a number, which is also called, it's actually also called a bias. Okay, so it'll multiply those two vectors element, make a dot product, then add the bias number. That's also an input here. So there were 3 inputs, and then let's say bias happens to be 0, then you just do this. Okay, 19 plus, and then apply a nonlinearity. That's the operation going on in a node. Okay, now I'll tell you what these vectors are. Back to how are they related to this W1 W1 B1 W2 B2. These matrices and these vectors. Okay. And so this is what a node typically does, and the difference between CNN and feed-forward network or FC and fully connected network, it's the same name. Okay, it's going to be that the number of parameters is reduced. Okay, so this is going to be a key point. So we're going to introduce a new layer. So far we've only seen a simple layer, a hidden layer, and we'll actually now I've defined a node, and we'll revisit what that layer is. But for this section, for the next 15 minutes, what we want to take away is that, hey, there's going to be a different description of a layer. So it will have its own nodes, and those nodes are somehow defined such that the overall number of parameters is somehow reduced. Okay, the overall number of parameters. Okay, what are parameters? These are parameters. So I'm going to relate these parameters to nodes. Okay, that's what I'm going to do in the next few minutes. By the end of this lecture, end of the session, you should be able to say, hey, the number of parameters for a convolution layer in particular is reduced. Okay. So let's come back, let's take it one step at a time. So let's talk about feed-forward neural network. Okay. The feed-forward neural network, as I said, given a vector x little I. Okay, little I just corresponds to okay, let me not even put little I here. Given a vector vector x, let's say it's one training observation. So there's a feature vector x. Okay. From the feature vector x, I need to get to a score vector. Okay, let's call it S if you want. By passing through a sequence of hidden layers. So once x is given, and this is exactly what was happening, right? Once x is given, I'll do W1x plus b. Sorry for that. Let me W1x plus b. Wow. Then I'll do the nonlinear operation. This is max of 0, something. Then I'll do W2 of whatever that about thing was. Let's call it h maybe. W2h plus b2. And this was, these are the sequence of transformations. And maybe this is equal to the score vector. Okay. Right. So Yeah, sorry, I was trying to get the chat up so that in case I miss any questions. And earlier, before the break, we saw that each hidden layer has a bunch of neurons or nodes. Okay. Now I'm gonna say how these neurons are related to these parameters. Okay. In particular, for example, W1 and B1 and W2 B2. Here is a figure, and I guess this is from Wikibooks. So here's the example. Let's say we have, let's say little n is equal to 3. Okay. Remember in our figure earlier, we had a 3-dimensional input. So I just wanted to make little n 3. So we have 3 coordinates. So my feature vector has 3 coordinates: x1, x2, and x3. Let's in fact let's drop this stuff. Okay. So in the first step, okay, when I multiply when I multiply the W matrix, W times x1, x2, x3. Okay, I'm gonna since this has to be multiplied, this the matrix, the number of columns has to be 3 because the input is 3-dimensional. Now let's say the number of rows is 4. Okay, 4 cross 3. That's the number of hidden neurons. Number of hidden neurons is 4. Let's pick the first row. Let's focus on the first row. Okay, so that's going to be W11, W12, W13, W14. Okay, first index being the first row, second index being which column, which column you are in. And actually, I made a mistake there. It should be W1, W2, sorry, W11, W12, and W13. And there are only 3 rows, right? So row 1, sorry, there are only 3 columns: column 1, column 2, and column 3. So you can see if I do this, I said there's a neuron 1, neuron 2, neuron 3, and neuron 4. There are 4 rows. So each neuron basically is related to each row of this W matrix. Okay. So neuron 1 will basically say, hey, give me 2 vectors. The first vector is going to be W11, W12, W13, the first row of this W matrix. And also give me the x input. That's also x1, x2, x3, the 3 coordinates of my feature vector. And I'm just going to do a dot product. And dot product is exactly, hey, W11 times x1 plus W12 times x2 plus W13 times x3. Right? That's what a dot product is. Okay. But that's exactly what's being shown here. So x1 will be multiplied with W11. Okay. Actually, this notation is a little bit different. So let me change these guys so that it's not confusing. W11, W12, W13. Okay. And let's call this S. Yeah. And let's not worry about this stuff here. Yeah. So x1 gets multiplied with W11, x2 gets multiplied with W12, x3 gets multiplied with W13. We are really like going at the level of multiplications and additions. Okay. So once we do this, there's going to be a summation. Okay. So which exactly is this, right? So this is actually equal to W11 times x1 plus W12 times x2 plus W13 times x3. Okay. And then an activation function. Just think of this as max of 0, comma, whatever is the input. Let's call this z. Okay, let's call this z. And that's the score. Is equal to score. Actually, it's not score because let me not call this score. Yeah, let's say this is called output for layer 1. Output for layer 1. Sorry, output for neuron 1. Is this clear? So I just really broke down the we were doing wx plus b, w1x plus b, b1 as the first operation, right? In this one hidden layer neural network that we had a few slides ago or right before the break. I'm just saying that each row is basically associated with a neuron. So how many number of neurons do we have? is basically the same as the number of rows that we choose for the W1 matrix. Okay, and therefore, since the number of rows related to the number of neurons, so each neuron should be related to each row of the W matrix. Okay, and similarly, there's going to be in B1, there's going to be B1 1, B1 2, 3, and B1 4. Okay, so this guy is going to be this B1 1 is going to be related to the first neuron. B1 2 is going to be related to the second neuron, and so on. Okay. So if you come back to this picture in the previous slide, vector 2, let's say, is the x, three-dimensional x, x1, x2, x3. Vector 1 is going to be, let's say, the first row. Let's talk about the first neuron of the 4 neurons. The first neuron will be related to the first row, which is W11, W12, W13. And there's going to be a bias, which is going to be the first coordinate of the bias vector. Okay, given all of them. Okay, sorry, here it was not three-dimensional. Here it's two-dimensional, but all of them, you just do a multiplication this way, which is it is a dot product between the two vectors. Okay, whatever the sum, and then plus bias. You add a number, and then take this activation operation or activation transformation, nonlinearity, whatever you want to call it, and then that's the output of this neuron. Okay, and so there's going to be 4 outputs because there are 4 neurons. Okay, now we have a 4-dimensional activation vector. Okay, that's the output of the first. That's the output of the hidden layer. Okay, so and then that activation vector, let's call that, we were calling it O1, O2, O3, and O4 because there were 4 neurons. That times the W2 matrix plus B2 is basically the scores in the one hidden layer neural network, a feed-forward neural network case. Okay. So any questions about this? I know I've not used numbers, but I've used symbols here. But if you want, I can use numbers to again explain this. But let me know if you have questions at this point.
Professor, it would be great if you can have an example with numbers. It should be nice. Yeah, thank you.
Yeah. So okay, so let's go back to our original. Okay, actually we have the picture here. So let me see if I can use the next slide. Yeah. So we had this figure, right? So we have already said, hey, this is a 1 hidden layer neural network or a 2-layer neural network. There's 4 neurons: neuron 1, neuron 2, neuron 3, neuron 4, right? And there's 3 inputs. So the dimensionality is clear. So there has to be 2 scores, score 1, score 2, that has to be produced. Input is x1, x2, and x3. And I'll put numbers in a second, but I just wanted to put things. So let's call this O1, O2, O3, and O4. Okay. Now, I'm just saying O1, O2, O3, O4 because that's what I wrote here. Okay, the output here is O1 for the first neuron. So let's actually look at what the first neuron does. So okay, I'm just focusing only on the first neuron. So there's 3 edges like this, 1, 2, and 3, and there's a neuron like this, and it's producing. It's going somewhere, but let's call it O1. Okay, so let's only focus on this neuron here. Okay, so what I did is I ignored this guy, this guy, this guy, this guy, and this guy. So now what I'm trying to say is that these edges are related to W11, W12, W13, and these initial inputs are just x1, x2, and x3. Okay. Now to put numbers here would be, let's say my feature vector is 1, 2, and 3 for simplicity. Okay, and let's say my weights happen to be this. Okay, so let me just put simple weights here. Some bunch of numbers. It doesn't have to be ones, but ones make it easy for me to compute. Okay, plus I'm gonna do a bias, which is 2 and 2 and 0. So this is B1, this is W1, and this is, let's say, X. Okay, X is some training example. So one feature vector for one observation. You want to do this for all observations and so on, right? So now what I'm trying to say is that this anyway you can compute, right? So I can see, hey, 1, 1, 1 times 1 plus 2 plus 3 is 6. Second one, 1 plus 4 plus 3 is 8. And 1 plus 2, 3 plus 9 is 12. Okay, and then I had to add 2 here. So actually, let me erase this. 6 and 8. Instead of 6 and 8, it will be just 8 and 10. Okay. This multiplication, anybody can, you can do it, right? It's just a matrix vector multiply plus some addition of a vector, right? So what I'm trying to say is that, hey, let's focus on only this number 8. Okay. So how did 8 come about? 8 was equal to basically take the first row of the W1 matrix. Why did I choose 3? Okay, let me actually add one more coordinate here. Let's call it 2, 2, and 2. So I wanted to keep the, so actually I want to have 4 rows. Okay, sorry about that. So I'll produce one more number here. So 2 times 2, 2 plus 4 plus 6. 12 plus 1 was 0. Yeah, so let's say this is 12. Okay, so therefore, I wanted to have 4, W1 to be actually 4 cross 3, and X is to be 3 cross 1. Just, all the examples should line up. So sorry about that. So, okay, this is what I wanted. Let's just focus on the first row of this W1 matrix. Okay, it's just 1, 1, 1, 1, 1. And the input is, as usual, 1, 2, 3. Okay. And I'm just saying, let's look at only the first coordinate of the B1 vector, 2. Okay, so this is clear, right? 8 is equal to 1 times 1 plus 1 times 2 plus 1 times 3, right? Plus 2, right? That this is clear. This, what I'm saying is this computation is related to the first row of the 4 rows, and the first row output is basically the intermediate computation of the neuron. Okay, so 8 is, the story doesn't end there. Once you compute 8, what you do is you also do apply the nonlinearity. Okay, let's say one nonlinearity is max of 0, the second argument. Okay, so the second argument for me is 8. So this is equal to my O1. So just zoom out so that everything is visible. I know for some of you maybe it's clear, but for some of you who wanted to see some numbers, so this would be one computation. Okay, this is the computation of the. So this is O1, but similarly O2 would be again max of 0, 10 is going to be 10. Similarly O3 is going to be 12, and O4 is going to be 12. So why do I say O1, O2, O3, O4? These are the 4 neurons, and each neuron's output is this. Okay, first neuron's output is 8, second neuron's output is 10, and so on. Okay, because I have only 4 neurons in my figure here. Okay, there are only four neurons. So, so is this clear? So when I say, so each neuron is basically taking the weights vector and the input vector. It doesn't have the input vector itself, but because these neurons, is the first hidden layer, and so it sees the input. But if it's the second hidden layer, it will not see the input, but whatever is the output of the previous layer. So that's some extra information, but everything else remains the same. Okay, the same. It doesn't have to be input. All I'm saying is input to this layer. It does not be the original input feature vector. And this is exactly the computation happening. This plus the nonlinearity is the computation that we ascribe to the neuron.
Professor, this is the first. This is the output of the first layer, and
Yes.
O1 goes to the
S1,
output.
S1 and S2. Yeah.
S1 and S2.
Yeah. So now let's do that computation. Let's say for that I need W2. So W2, because there are only 2 classes, let me say W2 is 2 cross 4. Okay. And B2. Okay, let me just write this. Some example W2 and B2. Let's say B2 is 3 and -1, and W2 happens to be, okay, again, let me just choose some simple numbers. 3, 5. Oh, sorry, that's not. output. 3, 4, 0, 1, 1, 1, 2, 1. Okay, and this times any O vector. In my case, I have an O vector of 8, 12, sorry, 8, 10, 12, 12. Yeah. So this is going to give me my two-dimensional scores. Yeah, I mean, you can compute this, but I don't want to. So we can do it in real time, but so it's basically 3 times 8, 24 plus 40 plus 12. Okay, so 36 plus 40 is 76. Yeah, and you can compute plus 3 actually. I forgot the 3 here, but that's the first score 1. Yeah, and similarly, score 2 you can compute. So that's the second operation.
Okay. The dimension of W1 and W can be different as I see it here because of.
So W1, one dimension has to be restricted, right? It has to be the input dimension, whatever is the input to it. The second choice, 4, was arbitrarily chosen. Why did we choose 4 neurons? Why not 5 neurons? Okay, why not we put 5 here? We can do that. Okay. But the dimension of W2 also, one side is fixed because I have a 2-class classification. Let's say one of the dimensions is fixed, right? I can only, yes. I can even produce 3 rows, but the third row is not going to be useful for me. But the 2 is fixed, but this is our choice. But this our choice is, of course, we don't have too many choices because this 4, the hidden layer, once we pick the number of hidden neurons, both W2 and W1 know what the dimension are.
Yeah, got it. Thank you, Professor.
Okay. So this is, I guess, this part was just trying to explain what is. So this is called a neuron. Okay, and this has some historical, I guess, terminology usage. So this was. So in 50s and 60s, folks wanted to replicate, the computation in the human brain, and we are still trying to do that. And so the base unit of computation here is this thing which takes 2 vectors, like the x's and w's, and multiplies them coordinate-wise or whatever. Some products, some, and a sum is happening there, right? So that's a base unit, and so and that with analogy with biological neurons, or at least inspired by biological neurons, folks just named it as a neuron. Okay, but it's basically just a computation node. We don't really have to think of neurons as related to biology. Many of the neural networks that you'll see in this class, they may be inspired by some operations in biological neural networks, but there's not much resemblance actually, and people are actually still working on trying to relate those two and also improve neural networks, artificial neural networks, which is the subject of this course, to maybe mimic biological ones, with the hope that maybe if you mimic that, maybe they have better properties. But then the terminology is just historical. Why call it a neuron? It's just basically a node with just as dot product plus a bias, each node. So if upload these annotated slides, okay. Okay, I need to remember this somewhere. Let me just write it immediately.
Thank you, Professor.
But you will be able to see at least the slides on the video for the time being. So hopefully at least you have that part. But yeah, I can upload it. Actually, last time I was using the class notebook feature. I don't know if any of you used the class notebook feature in OneNote, but turns out that nobody used it, so I just dropped that this time. But maybe I can certainly share the slides, the annotated slides.
Thank you, Professor.
So let's actually move towards CNNs now. Okay, so now we have a good sense of layers for at least the feed-forward neural networks. So now the only change that we're going to introduce is to define a new layer called a convolutional layer, and also one more operation called pooling. Okay, essentially there are only 2 things for the remaining half an hour, or maybe if it spills over to the beginning of next session, only 2 things to take away for how CNN model class is slightly different from the feed-forward neural network model class. In feed-forward neural network model class, the only thing we can do is increase the number of layers, increase the number of hidden layers, right? Although in the example we only saw 1 hidden layer, we can just make it 2 or 3 or 4 or even 10, and people have done that. Okay, people wanted much more wiggly functions or more complex functions. These are not linear functions anymore, so they're more complex in the sense that they can capture much more complicated patterns. If you keep on adding a lot of layers, for example. So there's not too many things that you could choose. You can just choose a number of layers, and maybe you can choose the number of neurons in each layer. Okay. Now what we are getting now is the next building block, which is a type of layer. Now now you can imagine that now if I define a new layer, you can now start doing a lot of things. Right now you have two types of layers. The regular layer that you saw before is just called a fully connected layer. Okay. And the layer that we're going to see now, which is called a convolution layer. The moment you have two types of layers, you can do several things. You can say, hey, I'll first pick a fully connected layer, next a convolution layer, next a fully connected layer, next a convolution layer, for example. That's one pattern. Or I can say, hey, I'm going to start with convolutional layer, followed by a convolution layer, followed by a fully connected layer, followed by a fully connected layer. So there's so many things that you can do the moment you have layer types, right? So that's where you get into more choices to make. And this choice explosion, curtailing the choice explosion, I guess, for at least applied practitioners, it just depends on seeing what are established popular design choices that tech companies or these research labs which are pioneering work in deep neural networks are choosing. Okay, so they at least give us some guidance on, hey, maybe you should use con layer followed by let's say linear layer, for example. So this is an example. All I'm saying is these folks have the people pioneering these models have some set of empirical rule of thumb choices that they made, and they've also defined full example such model definitions, and we'll just pick them even if we have a slightly different problem or a specialized problem in our business setting, in our applied setting. So sorry, that was just a quick comment about that we're going to look at one new layer essentially, and one more extra, I wouldn't call it a layer, but one more some sort of a nonlinearity step. So here's an example of data set, and you'll see this data set, I think, as part of assignment 2, where you will try to use Collab and this data set to, again, basically do classification. So this is actually a 10, CIFAR 10 is the name of the data set. And as it says, the 10 represents actually 10 classes that are present. So there's also CIFAR 100 data set, which has 100 classes, and so on. And it has basically this sized images, okay, 32 times 32 times 3. So 3 because there are 3 channels in the image, a red channel, a green channel, and a blue channel. And 32 cross 32 is the number of like pixels, 32 pixels wide and 32 pixels tall, okay, or height. So here are some pictures from each of the, I mean, you can't really see, in that well, but because they're really small figures, but you can see that these basically look like automobiles. So what I'm trying to do now is just motivate why we need a con layer, for example. So let's say we didn't have con layer. We have these images and we want to do 10 class classification, right? One choice that we just saw fully connected layers of whatever feedforward neural network. Let's start with feedforward neural network, right? So maybe we can have, some hidden layers and some hidden neurons, some number of hidden neurons in each of those layers. So what would be like, then that means that my X, I have to somehow make it as a vector. So although I have an image, which is 32 times 32 times 3, I have to vectorize it because, in fully connected or feedforward neural networks, we never thought about any shape for the input, right? It was just a feature vector. Like in a running example, it was 3 dimensions, but it's just a feature vector. It's a vector. So that means we just multiply. So multiply as in like we vectorize our image. So we basically, we have a cuboid type of a shape of numbers, right? Numbers are arranged in some sort of a cuboid shape where there is a matrix followed behind a matrix and then another matrix, each matrix for each of the 3 channels, red, blue, and green. We can just put the numbers, stack them together, basically concatenate them one after the other in some way, maybe row after row after row after row, and the next matrix and all that. So ultimately, you'll get a vector which is of this size, right? 32 times 32 times 3. And so if X is of that size, then for each neuron, there has to be corresponding W's of that same size, right? Because we saw in a neuron, it takes X, at least the neuron which is right next to the input, in the sense the first hidden layer, that neuron has to have those many weights. And similarly, if I have 10 such neurons, it will be 10 times those many weights. Plus, each one bias parameter for each neuron. And you can already see that, hey, if one neuron, so how much is 32 times 32 times 3? So you can say it's 2 to the power 5 times 2 to the power 5 times, let's say 3 or 4, doesn't matter. So it's 2 to the power 10, okay, which is about 1000, okay, 1024 times 3. So whatever it is, 3072. So this is the dimensionality of the input. Okay, so 3000, feature coordinates, and so one neuron has to have 3000 now parameters. Okay, 3000 parameters. And if I had to 10 neurons, it's like 30,000 total parameters, right? Plus biases as well. But what if the image size is now much, it's a little bit bigger? Okay, this image size is basically the size of your laptop screen, right? I mean, the sense the number of pixels, for example, in a ultrabook that you may carry, will probably have this much, resolution. Okay, or let's say image is this resolution. It's basically about a 1 megapixel, right? 1 megapixel image. Okay, implies that each neuron in the first hidden layer needs to have about 1 million parameters. Okay, and the moment you have 10 such neurons, or maybe 100 such neurons, already 100 such neurons times 1 million in each neuron is already 100 million. Okay, so 100 million numbers will occupy a ton of memory space in a regular computer. Okay, so you're already like hitting a lot of computational, limits, or some sort of your resource intensive, if you want to use a fully connected layer with images. So, one way to fix this, is to fix this explosion. What are you fixing? Fix this explosion in the number of parameters needed, is to do some sort of a clever parameter reuse. Okay, so clever parameter reuse. Okay. And you'll see that the con layer eventually, if you don't take away anything else from the rest of the section, a convolution layer or a con layer essentially does this. Okay, it's just some sort of a way to reuse parameters. Okay, which means that, hey, if there's a parameter W11, W12, W13, let's say, they somehow are reused in the sense that they are used for multiple neurons. Used for multiple neurons. It may not make sense much at this point because I haven't even told you what the convolution layer looks like. But at the back of your mind, this is what is happening. Okay, and now we'll get into some some level of details about like what is this parameter use and how does a con layer look like? How does a neuron in a con layer look like? Okay. So starting point is going to be, again, we'll talk about layers first and then look at the neuron, just like we did with the feed-forward neural networks case. Okay, so we'll look at layers first and then the neurons themselves. So the first, conceptual, this is all about diagrams. Okay, the underlying functions are just the same functions, whatever they are. We have not seen the function for convolutional neural network, but at this point we don't want to look at those functions. We just want to get a diagrammatic picture of what is this model. How is it different from for example, the feed-forward model, the feed-forward diagram. Okay. The new idea is that layers will have width and depth. So you may say, hey, how can layers have width and depth? The simple idea is that, previous diagrams we saw neurons or nodes one below the other. Let's try to stack the neurons next to each other, in some sort of a matrix or in some sort of a spatial way. Okay, instead of just one below the other in the diagram, instead of one below the other, let's put it next to, like maybe horizontally next to them or vertically next to them, so that they occupy some space. Okay. So feed-forward networks, as you saw, only had heights, like something like this, right? So instead of this arrangement that we saw in feed-forward networks, we'll try to change this. Okay, and this depth is not the same as the number of layers. Okay, so in feedforward networks case, it is just, I guess, just a side note, that in feedforward networks case, if I choose 10 hidden layers, then it's like and that's where the name deep neural network comes. If I choose 10 layers, that's considered deep, right? So that's why we call it deep neural networks. But here, this is just a notion of depth for the layer, okay, not the depth of the network itself. So we're gonna talk about individual layers and then having some depth and also having width. Okay, so previously they only had height. And this is the arrangement. So they only had neurons were one below the other. We're gonna stack them such that they are in a matrix fashion or in some sort of a cuboid fashion, okay, or it's also called a tensor. Okay, let's actually look at that. So this is what we saw before. And now I'm saying, hey, because input is an image, let's keep the image as is. So we know that, for example, in CIFAR10, it's 32 cross 32 cross 3. So actually it doesn't, so this, and I'm saying that the input numbers, I'm going to just represent them as some sort of a cuboid here, or some sort of a, some sort of a cuboid. Okay, so this, all the circles are basically just this small things that I drew. Think of them as cells, right? Image, if you think of image as this three-dimensional object, there are numbers, there are 3 numbers one below the other in the depth direction, and there are 32 numbers one below the other in each, in each like channel, basically in the height direction, and similarly in each of the width direction there are 32 numbers. One thing is this is actually a cuboid, okay, with a depth of 3 with a height and width of 32 cross 32. Okay. Similarly, all I'm saying is, hey, on the hidden layer side, let's also rearrange. So moment we have like, let's say I have 27 neurons. I can do 3 times 3 times 3, right? I can make it into a cube, for example. So similarly, whatever the number of neurons here, I'm gonna reorder them. Let's just repackage them so that they look like a cuboid. Okay, so that, for example, can be a hidden layer. But that's not I'm just giving you an analogy of this view of a single, this layers now become cuboids. Okay, and so the score vector also becomes a cuboid, but we know the score vector has to be just score 1, score 2. Let's say 2 class classification, there should be only 2 numbers. If it's a 3 class classification, score 1, score 2, score 3. So only 3 numbers. So let's say the score vector has some depth, which is the number of classes, and height and width are just 1 cross 1. So that's also cuboid. So we just saying everything is now a cuboid, okay, or a tensor. Yeah. So what I said is exactly this. So for feed-forward layers, this rearrangement of neurons doesn't mean anything. Okay, we know exactly what each neuron does. Each neuron is associated with a bunch of weights and a bias value, and it does exactly this dot product plus bias and some nonlinearity. We know exactly. So for feed-forward neural networks, this cuboid picture doesn't get us anything. Okay, but for convolutional neural networks, this cuboid way of looking at the diagram of these layers of this model gets us some intuition about this parameter reuse. Okay. So this is what I meant. So ultimately, we'll have a cuboid like this, okay, for associated with each layer. Okay, and so now we are explicitly not saying hidden layer. So these are, anything which is not input and output layer is basically hidden. So let's not explicitly talk about hidden layers, but they're going to be layers, and these layers can be looked at from a point of view of thinking of these are cuboids or tensors. Okay, and so going from when going from input all the way to output, I can think of my input getting changed. So input, by the way, itself is a tensor, right? It's 32 cross 32 cross 3. It's a tensor or a cuboid already. So that input is going to get transformed to another cuboid. Maybe one more cuboid, maybe one more cuboid. And then finally, I get the final cuboid, which we saw is just, I just said here, it's number of classes times 1 cross 1. It's also cuboid. It's a degenerate cuboid in the sense that there's no height of it, basically, but it's a bunch of scores, which is the number of classes, for example. So you just need to think of the transformations, this layer-wise transformations happening as going from a cuboid to a cuboid to a cuboid to a cuboid, and eventually a bunch of scores. Okay. Okay. So we have very few minutes, so let's spend some time on this cuboid idea. So as I said, let's say our input is 32 cross 32 cross C for this specific data set. It doesn't have to be this exact number, but for us, let's have this as a number. And as I said, final output is going to be 1 times 1 times 10. Okay, 1 width, 1 height, and 10 as a depth, because we have 10 classes. It doesn't have to be exactly this. You can change the, for the output, you can just, change things if you want. But this is the input, this is the output. Okay, those two are cuboids. Okay, so if input is a cuboid, output is a cuboid, intermediate processing, intermediate, things that we produce will also be cuboids or tensors. Yeah, so if we have two hidden layers, let's say we have two hidden layers. If the regular picture with the feed-forward neural network, if the picture would look like this, if the diagram of the network would look like this, input layer to a hidden layer 1, hidden layer 2, output layer, okay, then the figure, the diagrammatic picture of this model would look like, hey, this cuboid to this cuboid to this cuboid to finally a score vector. Okay, and as I said, these cuboids have, what are these cuboids? These are some numbers. So cuboid is basically a bunch of numbers, right? So you can see in this diagram, these circles just represent, hey, there's some number residing here. At the third coordinate on the height, on the second coordinate on the width, or maybe on the fifth coordinate on the depth, there's some number. So it's basically a bunch of numbers stacked as a tensor, right, with 3 indices. So you can access, let's say, the 10th index, the second index, and let's say the 5th index, something like this. Then this will be some number equal to 9. So what are these? These are the indices. Okay, let's say A is a tensor which is let's say 32 cross 32 cross whatever 10. Some cuboid. I didn't want to use exact numbers, but okay. So pick the 10th index on the first coordinate, and the second index on the third coordinate. Pick the 5th index on the third coordinate. And you get a number. Okay, let's say some number 5. So this is a cuboid. So now these circles are numbers, but we just saw for the feed-forward case that the circles also represent neurons, okay, or neuron output. So whenever there's a neuron output, there's also a neuron. Neuron output is generally a number. So of course, that if there's a number, there's going to be a corresponding neuron related to it. So that neuron, you can represent it using these circles. Okay. So whether you talk about a number or whether a neuron, it's both basically the same thing, okay? Because the neuron is what produces a number. Okay. And I said earlier that each layer can basically transforms an input tensor to an output tensor. So given this input tensor, this is the output tensor, or let's say the first layer. And similarly, for the second layer, this is the input tensor and this is the output tensor. And finally, let's say this is the input tensor, the one here, and this is the output tensor for the last layer, the output layer. Okay. So this is the input layer, this is the first layer, this is the second layer, and this is the output layer, where this is the output. Yeah, and as I said, each layer just transforms an input tensor to an output tensor using some function. So we're going to spend now time on, hey, how am I getting a tensor, and why does the tensor or cuboid idea help me in any way? Okay, so that's the crux of what we want to get to. And as I said earlier, we have seen fully connected layers before. For fully connected layers, or the usual layers that we saw in feed-forward neural networks, this cuboid idea is kind of redundant. It doesn't matter whether you arrange the neurons in a cuboid shape or in circular shape or whatever. A neuron is a neuron, and we know exactly, there's going to be weights associated with it and a bias, and we saw that clearly. Okay, even if we had some shape, we can always put the neurons one below the other, and we know exactly how each neuron should behave. Okay, so we have seen this, but what we're going to introduce is two new layers. Actually, the second one is not that complicated. It's a pretty simple layer, but the main thing is going to be this convolutional layer. And once you have so many choices, you can, as I was saying earlier, you can now think of a deep network where you have layer 1, layer 2, layer 3, layer 4, layer 5, let's say layer 10. Now each choice of the layer 1 to 10, you can pick among 3 things, right? Then that really increases the number of model descriptions that you can have, or different types of models you can have. Forget about the parameters themselves, but even the model definitions, there are so many models, right? Okay, so yeah, I think yeah. So actually, let's go through this example. I'm purposely going a little bit slow here rather than rushing things. We'll pick up again the definition of the con layer potentially next class if we don't get to that in the next few minutes. So here's an example architecture. So let's say we still want to do this 10 class classification on this particular data set, CIFAR10, that you'll see in assignment 2. Here's an example architecture. You have the input layer. You pick the con layer as the first layer. We pick the pool layer as the second layer. We pick the fully connected layer as a third layer. And then we finally get scores. Okay. Actually, yeah, let's say the fully connected layer itself produces scores. Okay, so let's just call this the output layer. Now input we know is 32 cross 32 cross 3. That's a cuboid. Okay. This we know. So the con layer is what we have to define still. Okay. This con layer will also have neurons. As I said, anytime we have a tensor or a cuboid, there are cells or numbers in it, and each of those numbers should be related to some neuron. Okay. So there's going to be so even if it's a con layer computation, at the end of the day, there's going to be some numbers output, and each number output is actually related to a con layer neuron. Okay. So convolution layer neuron. And the neurons, in fact, actually do the same thing. It turns out that neurons exactly do the same thing. They just do some of the products of the inputs with some appropriate weights and add bias. And this is now, if they do exactly the same thing, then what's the difference? The difference is that for feed-forward neural networks, we had weights associated with each neuron. They were not related to the weights associated with other neurons. Okay, so for example, row 1 weights were associated with the neuron 1. Row 2 weights were related to neuron 2, and so on. Here, we'll see that there will be multiple neurons which will use the same set of weights. Okay, and that's the key idea behind this parameter reduction. And also, there are some side benefits, which is that the way these neurons are defined and the way they reuse weights, they actually exploit some properties of the images. Okay, some sort of, hey, in the image, whether the cat is on the bottom left or the bottom top right, doesn't matter. You need to still pick up that some sort of a pattern of that cat. And so that spatial invariance, for example, is something that this layer can deal with because it's reusing weights. Okay, but we'll talk about that in the early next class. So anyway, so the con layer, let's say, produces some size tensor. Let's say 32 cross 32 cross 12. Okay, 32 cross 32 cross 12 is the output of this con layer. Okay. Then what you do is, let's say since we picked the pool layer, this 32 cross 32 cross 12 is just or not just 12, but all these 3 numbers were something arbitrarily chosen at this point to just illustrate the example. So this is the input to the next layer, pool layer. The intuition for the pool layer is that it just has to somehow shrink this cuboid. Okay? So if you think of a cuboid with 32 numbers on the horizontal axis, 32 numbers on the vertical axis, and maybe a depth of 12 numbers, what pool layer does is somehow shrink on the depth and so shrink on the width and height dimensions. So it will keep the depth the same. So it will keep the last number unchanged. So 12 remains 12. But somehow goes from 32 numbers on each dimension to half those numbers, for example. Okay? Somehow like pooling or shrinking the size of this cuboid, like it's really compressed the cuboid. So there is a question. Okay, so there's a question that does that mean that W11 is handled by one neuron in con layer? So roughly, and we have not got into this yet, Supriya. So it means that W11 is handled by more than one neuron in a con layer. Okay, so in the fully connected layer, W11 is only connected to, let's say, the first neuron in the hidden layer, right? So here it will be used by more than one neurons. We'll see that. We'll actually spend some time on this, understanding that.
Okay, Professor. Thank
you. Yeah, and let's say it somehow squeezes, and if you think of a bread, a loaf of bread, and you're like shrinking it both on the height and width. Now you have a different loaf of bread, basically 16 cross 16 cross 12. Then the output layer here would just, hey, you have these bunch of numbers. Let's just if we have a fully connected layer, it doesn't really care about the shape of this cuboid. So just vectorize this. Vectorize this and gets to this 10 class score 1 all the way to score 10. Okay, so vectorize just means if you have any cuboid, just pick a pattern the way you can stitch these numbers together into a single vector. Okay, that's what it means. If you have a matrix, vectorizing that means, hey, pick the first row as the first set of numbers, let's pick the second row as next numbers, just concatenate them vertically. Okay, that's vectorization. Okay, so that's the last layer. Okay, so that basically gives you 10 numbers, or basically a cuboid, which is 1 cross 1 cross 10. So that's an example architecture, and here we have the same picture. So input, con, pool, fully connected. Each of them will have a cuboid associated with them, and wherever a cuboid is, there's going to be neurons related. Each cell in a cuboid is essentially a neuron, except for let's say the input cell or the output cell. Output scores and input the image. Okay, and these each of these is a neuron, and con layer has a special property that the neurons, the weights related to the neurons, they're not unique to them. So multiple neurons will use the same weights. Okay, that's one key idea. Okay. And we'll see a few ideas related to this next time in the class. Yeah. And again, once you have this, once I tell you what the neuron looks like, and what is how is this reuse happening, once you figure that out, there's going to be still again a bunch of parameters, some weights, just like for fully connected layer, we said, hey, there's going to be W comma B. Similarly, for con layer, there's simply going to be some W prime, B prime, or some other set of W's and B's. Again, the idea about optimization is to backprop and choose the best choices of these guys, which gives us the lowest, let's say, classification error, or or the cross entropy error that we saw earlier. Okay. So with that, let me conclude for today. And so just to recap, what we saw is we looked at the definition of feed-forward neural network, and we understood the notion of nonlinearities. We saw the layer view, where the layers and the number of nodes or neurons in each layer, and so on. We also saw a quick demo on playground.tensorflow.org, as well as our own code on Collier. And then we started talking about, hey, how is con, now we started talking about, hey, let's now introduce a new layer, a con layer. And we're going to continue discussing about con layer next time. But the point is, this con layer is somehow has less number of parameters and is optimized for image data, okay, which is a certain type of unstructured data. So and we'll see that in early part of next class. So thank you, everyone, and I'll stop the recording now. And if there's some questions, stay back and please ask me.